So next, Norm Carlson, Zonge. So there's a paper, some of you, maybe, well, some of you certainly anyways, would have seen 1998, Northwest Miners.
98, I believe, yeah, 20
Right,
years.
so that's out there. So I considered this is another 8, so this is a 20-year revisit.
Yeah.
Will you be around for the 40th anniversary?
Yes, yeah, actually.
Oh, yeah, the controller is here.
I do it one more.
There's the laser, and the,
laser.
let's see, the first one.
You gotta push the first arrow.
All right, so we back up. And then,
Okay.
yeah, and then it will advance on its
All
own.
right.
Gotcha.
Okay. Yes, I may actually be around for the 40 years. I'm giving this talk for Scott Urquhart and Anna Szidarovszky. I've been at Zonge for 39 years. That sounds like a lot, but Zonge has an unusually long probationary period for new employees. In April of next year, they'll do my performance review, and I may become a full-time employee at that point.
Retired,
If I don't retire first. But yes, in 20 years, I may be doing this again with more modeling. But as I say, I'm actually giving Scott's talk. Anna did a ton of processing. I think she handed Scott 140 slides, and we've trimmed them down because of our time limit here. And we're basically looking at the new things that have been done with the silver bell data in the last 20 years since Mark wrote it all up for Northwest Miners. Just as a reminder, this is the silver bell, the overview view of it. Mark Thoman, he compiled a lot of this data, a lot of the geology. John Gilbert actually was the initial pusher for this, got it all started and suggested doing this at the Sarco. Sarco gave access to the site. They gave us basically free access to the North Silver Bell site that they had not yet mined. They had drilled it out, they knew it was there, but very little infrastructure, so not much culture. Just really an ideal situation. We were able to do complex resistivity. We did some CSAMT, reconnaissance IP, some time domain EM, and some very shallow time domain EM. We call it nanotem. But and then Sarco gave us the drill hole results, a lot of core samples to measure. Really just an excellent relationship there. Let's see, make sure I don't forget too much here. The location for Silver Bell, these are all of the different mines in the area, and well, Phoenix is up here, and actually the field trip, did you visit Silver Bell? Was that one of your spots? Okay, all right. But all the different mines, Tucson is in here, North Silver Bell. Silver Bell is the northern part of the Silver Bell mine. El Tiro and the oxide pit are the two things that have already been mined, and if I got the numbers right, the North Silver Bell part they'll get as much tonnage out of it as they did El Tiro and oxide. So very excellent site. This is the geology map from back in 1980. A lot of the reddish material here, which is a lot of it's what they call Alaskite, things like that. That kind of faded out over the years. Sorry.
Be careful of that connection, because it gets rid of red.
Okay. Well, and there's actually faded red in all of these areas, but you can see the general texture of the area, that structure there. Our study area here is up around the North Silver Bell deposit. The oxide pit is down here, Altero is here. So that's the area we're working. Our crew got in to do a lot of the data over different periods of time, but I think the very last survey they were doing, they watched the beginning blasting and took pictures of the beginning blasting for the pit. So we got in there, got the data, and got out literally just in time before it's all disturbed. Let's see. A little bit more on the location of things. I'll be careful with the cord. I'm going to talk real loud so I can actually see from down here. This is the sort of the infrastructure that's there now, the West Oxide Pit. There's the big tailings dams. We're working up here. That's the North Silver Bell Pit. It's now surrounded by national monument material. Kind of a controversial feature out here called the East Silver Bell Project, but that's been basically removed from interest because of the national monument. I think Zonge was considering putting this back into play, but at the last I heard is this is still out of play completely. So again, we're looking at this area up here, and this is recent aerial photograph, and this is the recent aerial photograph with a lot of the survey lines. We have lines running northeast, northwest, and then these almost east-west lines here. Some lines we did for the dipole part of the resistivity, or dipole part of the surveys. We did 250-foot dipoles. Some was 500. Some was both. This particular line, which we'll talk about the most, is done with 250-foot dipoles, 500-foot dipoles, and also with CSAMT, and then I think also TEM, but we aren't gonna talk about the TEM today. Airborne magnetics was also flown by World Geosciences as part of all of this, and as we mentioned, as several people have mentioned, actually North Silver Bell and Altero and sort of oxide are in a magnetic low, which contradicts some of the other things. This is a plot that Mark included in his talk. The enrichment zone is shown here, outlined in red. Propylitic alteration out here, potassic alteration in here, and of interest, especially to me, is the phyllic alteration. There's a narrow zone of phyllic alteration through here, and that becomes important as we look at some of these lines. The line that we're going to talk about the most is line 0, which is running right through here, and again, that was done with 250-foot, 500-foot dipoles, and also the CSAMT. And let's see. This is a comparison of the CSAM, the resistivity inversion model results from the CSAMT, which is on the top, and I know stations and depths are pretty hard to read there. This is the resistivity from the 500-foot dipole complex resistivity survey, and this is the IP data from the dipole survey. And I think we're seeing more detail in the CSAMT resistivity, but generally the same picture, the big low resistivity features here. The phyllic alteration that I talked about actually occurs in this area in here on about stations 7, 8, and 9, 7, 8, 9, and 10 of the dipole-dipole line. These are particularly interesting, high IP values in two different areas, one over the enriched zone, but one over the phyllic zone, outside the enriched zone. This is the dipole-dipole resistivity again, just what you just saw. This is the dipole-dipole IP, and this is a geologic cross-section put together from what they knew about it and our line position. You can see some of the dacite porphyry mapped out. There's monzonite, dacite porphyry, things like that. And this is the enriched zone. It shows up roughly where the lowest resistivities are in the different surveys. As we go further out here, though, beyond the enriched zone, we see this extra IP anomaly in that area. You'll notice also that the IP anomaly associated with the enriched zone actually seems kind of low, a little bit deeper than we might have expected. Then as we get beyond there, the enriched zone and the phyllic zone, we're getting outside the IP anomaly. One of the problems that we found in going back through the data and then all the historical data is, as Scott puts it, in some ways we knew too much about the area before we started. The lines didn't go far enough into background to make it really an ideal case. We're just barely starting to get into background out in here, and IP values go to near zero. On some of the other lines, it's the same way. We get some background out here in the dipole-dipole line and the CSAMT, but to be an ideal case history, you'd really like a lot more background to see how variable background is relative to your anomalous area. What we've done here is put together the different lines into a 3D view. So this is CSAMT data we're going to look at first. So the resistivity sections from the CSAMT data. That went a little fast, but there's CSAMT line 44, then line 36, 28, 20, and then getting down to line 12. And actually things hold together pretty well. The low resistivity zone holds together quite well, and when we start adding in the dipole-dipole lines, those actually show good correlation as well. These are the IP sections, but it's the resistivity data from the dipole-dipole data, so kind of ignore that particular label there. But there's line 0, which we've looked at before. That's the low resistivity zone in line 0. This is where we're getting out into the phyllic zone. Then when we add in the other lines, there's one of the cross lines for that, and good agreement in there in the cross line, even though this is a real 3D environment. This is these are 2D model results along 2D lines, but in most cases we do get good correlation between lines where they intersect, which is sometimes kind of surprising because it is such a 3D world in this case. There's one of the other lines, again, showing up well. If we merge everything together, all that data, the low resistivities out in here hold together on all the lines. We see these changes in the middle where it's higher resistivity, and then resistivity is dropping off as we get farther away from the North Silver Barrel target. This is the IP data from the dipole-dipole survey. Here's the deeper IP anomaly that looks like it's associated with the enriched zone, but below it, this is that second anomaly associated, at least in map view, with the phyllic alteration. And then here we're getting into background there. Then the other IP lines, fairly good correlation here in where these two cross. and good correlation in the shallow data there. This high IP out here, we're getting closer to the El Tiro area. You see a little bit of a high IP out there. So again, things hold together despite the fact that it's a 3D environment. When we put the IP sections we just looked at, and we've rotated the view around a little bit, IP sections we just looked at here, and now we add in the reconnaissance IP data, it starts to fit the area as a whole. As we come down here, we're getting closer to the El Tiro deposit, and then further on down would be oxide. But each of these is where we took reconnaissance IP, or what Mark referred to as vector IP. These are all stations further out, and you can see that the IP data here in the vicinity of Silver Bell North is high. As we go further down towards El Tiro, it's even higher. And then outside, where we should have extended some of these lines for more background information, we see very low, near zero background that you would expect. So this is one of the reasons why we've done so many surveys that started with reconnaissance IP and then followed up with dipole-dipole or pole-dipole IP in the areas of interest. A good reason to do both types of surveys, especially since reconnaissance IP is such an economic tool for covering a large area. Usually these stations might be spaced 1 kilometer apart, something like that. Now, as I mentioned, ASARCO also gave us core samples from a lot of the drilling in the oxide area. What we're showing here are the complex resistivity plots. So low frequency ends up being out here, and this is these are the type of plots that back in the 80s with the it's the decoupled IP. In this case, you don't have to do much decoupling because this is a rock measurement, but fairly flat response, fairly low low IP response, range of 5 to 10, flat spectrum, what we would call a B-type slope. However, when we're into the enrichment blanket, much higher IP responses, over 60 milliradians, 48, 50, and we're starting to see more of the curvature in this area. And then if we go to the hypogene, we have kind of moderate IP response, and that's consistent with what we see at other sites, and some curvature to it. When we compare this to the dipole-dipole survey, where you're using 500-foot dipoles or larger, you have to remember that the Earth has the response. We have to take out the EM coupling type stuff, because really the total response that you measure out in the field, which Ken Zonge back in '72 made a perfect. Had made measurements out in the Wilcox Playa where he had a homogeneous low resistivity area, and when you go out to N of 6 and full frequencies, your curve ends up being that's the Zonge logo curve basically. But the total response you measure is the IP response that you're after, which is actually pretty small compared to all that EM coupling that you also have. So the goal has always been to separate the Earth response from the geometry of your survey to end up at a true zero frequency IP response. Now one thing that's nice is nowadays we're getting better modeling, far better modeling than we had back when we did the survey. So we can start modeling the EM response and the IP response combined. this is some one-dimensional modeling using the Scripps model. And all this is looking at is a comparison of 100 ohm meter half space, which is basically this blue line here. Everything here is in the air. Surface of the ground is up here, and then we have 100 ohm meter half space above, with and without a 10 ohm meter conductive basement. So the effect, basically we're just showing the effect on your data of just having a conductive basement down there ways, strictly from all of this coupling. And really the key thing to look at is down here, the huge phase changes, change in the amplitude. The phase anomaly here is in degrees. We measure ours in milliradians, so these are some horrendous. It looks like horrendous IP response in your data that's not actually IP. This shows how that effect hinges on distance from the transmitter, 5,000 meters from the transmitter, 166 meters. Big, huge change in the phase when as you move away, as your wires get bigger, all of that. So it's as much a reminder as anything. And that's what one of the things that is happening since all of this data was originally taken is us and other people that have taken the data set and used it for modeling are trying to use the complete data set, try to use the broadband frequency information that's there, because frequency response includes depth information, so it can extend the resolution of a DC model. And the IP response also has some frequency dependence based on mineral and grain size. And that was the source of tons of arguments back in the 80s. Practically fights at SEGs. One of the things that's been done is, these are some model results from Partha Rao from UBC, I think. Yeah. UBC took the entire data set, putting it into a model that does not contain the EM coupling, but he's modeling everything down to IP. Some of the geology from this is line 0, that main one we looked at. Some of the geology is shown here. The section is pretty stretched, so that's why it looks so different. Here's the enrichment zone, and he didn't include hour station numbers. He just has depth, has distance from the start of the line. But the enrichment zone, these are his model results of the resistivity data. Then chargeability. You can see in this area here, off to the east of the enrichment zone, he's starting to see higher chargeabilities in this area. Out there where we have some the dacite porphyry, and at the surface is mapped the philic alteration. Tau also shows some differences here as we go east of the enrichment zone, and then the relaxation constant, not quite as much change there.
The resistivity was markedly different from the earlier one, wasn't it?
Yeah. And because the resistivity just from the normal 2D smooth model inversion had this area is all pretty low resistivity.
Right.
Quite low. Yeah.
There's blue underneath
I
there.
got a question. What would a lot of kaolinitic clays do to resistivity?
Very conductive. Yeah. Makes things conductive.
But the resistivity?
Low resistivity.
It would be low resistivity.
Yeah.
So the difference, you're going from the leach cap into the hypogene sulfides, and then you go from high chargeability when you get to the hypogene, and you've got leach cap above it.
I just want to point out there might be some confusion because this is, the color scale is flipped from what you were using before. Red is resistive here, where before red was low
Oh.
resistive.
You're right, yeah. Okay.
So the conductor is actually in the right location.
The conductor is below the enrichment zone the way it was in that area. You're right.
This conductive zone shallower, it actually correlates quite well.
Right, and I think in the 2D smooth model stuff, there was kind of a slight increase in shallowest resistivities, probably because of the leach cap, but I'm not sure. Okay, yeah, you're right. I remember thinking that before and then I forgot it. Sorry.
Keeping us on our toes.
Well, somebody in the back is on his toes.
I'll mark it down in your performance review next year.
Yeah. That's not till April, so maybe they'll forget it, you know?
Well, Scott's sitting right next to me, so I don't know.
That is him, okay. And he's still making me give this talk. This is a test, isn't it? Let's see. Now this is the results of a Zonge inversion in which instead of reducing everything to coal parameters, what we've done is take each frequency, invert it to establish the correct inverted location in the cross section, and then combined all of those results at each frequency together so that we can put the IP curve at the right location in the model. That way we can look at these features and say, okay, what's the curve for that area versus this area. When we look at it in detail, for example, we have IP high, that's this area here, with basically a flat frequency response, what we used to call the B response. And then we have an IP high with decreasing imaginary component with increasing frequency down here. So this area here, which is in the area mapped as phyllic alteration, has a flat frequency response. The area here associated with the enrichment zone, or slightly below it, has what we used to call the C response. So we see curve-shaped differences between these two high IP areas. When we back out all of those frequencies and make a curve out of it for the right location. That's just kind of zoomed in. Those are the curves for that area. Down here, you can see it's more sloped as the IP high, it's a nice IP high, but as we go to increasing frequency, we have a slope in that direction. Again, that's what we're doing. We're trying to pull out the IP response from all of the other contributing factors. Some Zhu up at University of Utah, I think, also took the entire data set. So multiple groups have taken the whole data set over the years to try different models. This, I believe, does include the EM coupling, but this was the complete model of the complete EM IP response. Conductivity is up here, chargeability here. Again, this is all line 0. And then the relaxation constant parameter is here, time constant up here. And we're seeing things in the same area. The scale has been modified, so it doesn't look exactly like our plots, but it's interesting. Some of the features that we, for example, the phyllic alteration IP response that we were seeing doesn't show up there. What he also did was look at comparison these are now in these are section form. This is the lowest frequency, 0.125 hertz, 1 hertz, 40, up to 72 hertz. So those are the observed resistivities, and then 2D modeled. These are from his modeling the EM and IP. And you can see in resistivity, very good agreement between the original data and his results. So in modeling both EM and IP. However, for fitting the phase data, this is the original over here as we go from 0.125 hertz up to 72 hertz. His phase agreements are not there yet. There's still some still some things to figure out. Pretty poor fit, especially at the low frequencies. To summarize, people have been looking at this for almost 30 years. It's an excellent data set, and besides multiple methods of looking at the resistivity part of it, we have IP at multiple dipoles, and then we also have core measurements from drill holes within the area, within the North Silver Belt, within the enrichment zone. The latest generation of modeling tools is allowing the integration of both EM and IP data, and we're getting better at that, getting closer. Those tools will probably be even more useful once we're regularly doing distributed receiver systems and regularly taking true 3D data. As we have to keep in mind, these are all 2D lines, so we don't have true 3D data. There's no cross-line information here. So once we're doing true 3D surveys all the time, these newest inversion tools are going to be extremely useful. The limitations, as we mentioned, we didn't get enough background data. It would be really useful to have a lot of background so that we know the variability of background relative to our anomalous area. But too late for that. And all the data was collected before the advent of 3D acquisition geometries at all. So we don't have any cross-line data to throw into the new 3D models. And I think that's it.
Could you just comment on the physical properties, specifically with the supergene and the resistivities obtained with that? It was kind of early on. I forget what they...
Let's see.
You want to go get your images back?
Yeah. How do we get the...
I don't know if you can do that on that.
May not get it. Yeah, I'm not sure how much I can even comment on that part.
I can scroll through pretty fast.
Yeah, let me go there.
That connector came loose.
Oh, the dreaded colors.
Yep, now we got red. Drill on red.
Geophysical maps with two colors, blue and yellow.
Well, at least you know, Dick, if the geology falls apart, you can be the official plug guy. Here we go, sorry.
So,
Next one?
that's the oxide
Do you need to do it?
enrichment blanket.
Right.
Yeah. Yeah, well,
It's milliradians, it isn't.
these are in milliradians, and
So one that has all meters? I was interested in resistivity.
I don't think we had one with resistivity of the rock properties.
Oh, okay, all right.
Yeah, the resistivity numbers here range from, looks like lows around, well, there's one of 10, 140, 400, 1500. It's actually quite a range.
You can pick your poison.
Right, yeah.
Okay.
But it's all pretty high in IP. And this would equate roughly to chargeability, the milliseconds.
Right.
Yeah, so,
Okay, well, there's probably a tabulation somewhere.
yeah.
All right, good, well,
Okay.
thanks again.
All right.
That's great.
Okay.